Hello, everybody. My name is Frederic Bless, and I will moderate the lunch talk today. We have the chance to have Kevin Pahud today, who has done bachelor's and master degrees at EPFL in energy science and technology. Kevin Pahud did his master thesis with the consulting firm from Ocube, and he continued working for them for following project. And we're lucky to have him, and he will present his study. So, Kevin, if you want to start, the floor is yours.
Thank you. So, hi, everyone. So the purpose of the presentation today will be to specifically delve into industry decarbonization through electrification, and specifically look at the financials behind it with a focus on the Swiss industrial landscape. So before we start, let me just present quickly the authors of the studies. So I was the main author, and as Frederic presented, I did my studies at EPFL and continued working at the consultancy firm eCube Strategy Consultants with a focus on electrification and energy efficiency. Second author was Nicolas Charton, who is the director of the Lausanne office of the firm. And we did the study in collaboration with EPFL, Professor Rachid Cherkaoui, who is a power systems professor at EPFL, who focuses on grid integration. So let me just close this. Okay. So just a quick overview of what the firm does. We actually focus on energy, mobility, and climate stakes for our clients, whether it is private or public sectors. And we have different mandates, whether it is on energy, environment, mobility, infrastructure, or climate strategy and innovation. So as part of a project idea we had for industries, it was to underlook what industrial electrification meant for Switzerland. So a bit of context for Switzerland's landscape. So as a global overview, Switzerland's industry consumes about 20% of Switzerland's final energy consumption, but represents around 21%. And over the last few years, we've seen a decrease in territorial emissions for the industrial sector, as well as a decrease in final energy. And this was mostly due to a fact of switching heavy oil to natural gas in industrial processes, and as well as switch of specific industrial sectors, intensive to less intensive. And it followed by an explosion actually in the value added due to pharmaceutical companies being quite present in Switzerland. And so focusing directly in a detailed perspective on Switzerland's industry, first of all, on the energy side, we can see that around 41% of the sector is already quite electrified, with most of the electrification being done at mechanical work, so drives, processes. And we do have some electrification for process heats, which are mainly for the secondary steel industry, which only use electric arc furnaces. So there's quite some electricity consumption, and a little bit for non-process heat. And mostly we use gas in Switzerland, which is around 25% of full consumption. So in 2021 was around 11 terawatt hours. So it's still quite based on fossil fuels, as well as a lot of waste consumption due to the fact that we have quite big cement industries in Switzerland that consume a lot of waste, as well as pharmaceutical companies that focus on reusing their own generated plastic wastes. In terms of emission perspectives, the biggest sectors are the non-metallic minerals, so mainly composed of the cement industries. We can directly notice it with process emissions being the highest, followed by chemistry pharmaceuticals. So we have really big companies that produce either pharmaceuticals or chemicals directly. And it's followed by food, beverages, and tobacco, which is quite a big sector in Switzerland, especially tobacco that is produced in Switzerland. And these represent around 75% of all emissions in Switzerland and are really like the core sectors, and followed by metal and equipment, so watches, automobile parts, and other types of metal parts. And we can see that in terms of just energy emissions, the order is still approximately the same, which are the emissions that electrification will directly focus on primarily. So one might ask, actually, why should we actually electrify our end uses and not just use other technologies? So the idea behind it is to actually simultaneously reduce energy consumption because electricity is more efficient. And for the same given service, we could actually decrease the final energy consumption, and this would actually affect our infrastructure demands. So if we use much less energy, we would need much less infrastructure. And this would also impact a lot the supply of energy in Switzerland, which is quite dependent on foreign supplies of fossil fuels, since we do not produce at all fossil fuels. So, and we do know that Switzerland's grid is quite low carbon and that European Union's grid is getting cleaner. So we're at, I think, almost 70% low carbon in 2023, if I remember well. So that's the goal, really switch to electric-based technologies for the same process to reduce energy consumption and simultaneously decarbonize because of low carbon grid. So now that the context is presented, we can maybe look at what potential exists in Switzerland actually. So the idea is to actually look at the energy consumption behind each sector in Switzerland. So on the right part of the graph. And what is in green is basically what heat demand exists across industries. And globally in Switzerland, 64% of energy demand is for heat production. So this is where electrification will come in handy. And moreover, electrification is actually quite performant in low temperature sectors. So for Switzerland, we have around 20% of very low heat demand, so less than 100 degrees, and 20% again between 100 and 200, which is mainly steam production. And we do have to afterwards higher temperature demands, which are mainly heavy industries such as basic metals, non-metallic minerals, and chemistry pharmaceuticals for very specific branches. And if we look well, we can see that the food, beverages, tobacco, textile, leather, and construction sectors have quite low temperature demands, and the food, beverages, and tobacco sector specifically has quite a high energy consumption, which is the second highest, sorry, in Switzerland for heat demand. So we do notice that there is quite some potential, especially at low temperature sectors. And so when we define actually the electrification purpose of the industry, we really wanted to focus on a more realistic approach. So theoretically, we could replace all processes and just switch and electrify them all and get 100%. But that's not the idea behind the study. So first of all, we wanted to define specific stages of electrification. Stage one being actually just entry point electrification of non-process heat. So it's really heating buildings as well as hot water. So everything that is not related to the processes themselves. Stage two electrification is really electrification with more mature technologies. So what we would consider electric boilers or industrial heat pumps, and it goes up to 400 degrees. And stage three is more focused on technologies that don't have a high certainty of costs or technology maturity, and these go up to more than 1,000 degrees of temperature levels. And for after defining stages of electrification, we wanted to define where we could and could not use electrification. So the idea was to not switch existing low carbon technologies that were currently in place already. So such as industries that already use solar heat, district heating is already used, as well as wood. And we do have some industries that use quite a lot of wood. And also some industries have specific resource uses, such as I said previously, cement industries, they use quite a lot of waste. So as well as chemicals. So we didn't want to replace the waste consumption, even though it was fossil, because the idea was to really focus on not switching the whole economics behind these industries, as well as wood consumption, for example, for paper pulp production. And finally, there was a technology constraint that we applied, specifically heat pumps that cannot go up to 1,500 degrees. So there was a technology allocation on the electrification choice for our different sectors. And so the results that we found is that the Swiss industry could be electrified up to 73%, with half of it being already covered by that could be already covered by existing and mature technologies. So it's quite an important step and results. And 17% additional from non-mature technologies. And if we look well, the sector that has the highest potential is the construction sector, but it's a small sector in Switzerland in terms of energy consumption. So focusing more on the food, beverages, and tobacco sector, we really see that we're higher than actually 90%. So it's a really important potential that we have for electrification, especially with mature technologies. And it's also followed by textile leather, which is, again, a small sector. Fourth would be the basic metals, but this time we're really focusing on rather non-mature technologies because we're at much higher temperature technologies. And because it's because it's non-mature technologies, the potential for electrification is still present, but we'll see later on that in terms of economics, it would be much harder for competition. So yeah, basically, this is what to remember is that there was also a lack of data because of many industries. So the 73% could go a bit higher if we had more disaggregate data for the sector. But overall, we were at 73% of electrification potential. So what would this impact on the landscape, Swiss landscape? So in 2021, as stated previously, we were at 41% of electricity, with 35% being fossil fuels out of energy consumption, so around 15 terawatt hours. And through each electrification, we're able to actually reduce final energy consumption by 21%, while simultaneously increasing electricity demand by 7 terawatt hours, which is approximately 11% of Switzerland's annual electricity consumption. So it's not negligible, it's still present, so around 10% of increase. And what happens is that fossil fuels are basically virtually non-existent, with gas and light fuel oil being removed, the only remaining fossil fuels being very specific fossil fuels for chemicals industries such as naphtha or a little bit of coal for example, the ferrous industries, because we did not focus specifically on the process, just on heat production. So we do have quite an important result here. So reducing energy, our objective is reached while increasing electricity consumption. And as we can see, the highest electricity consumption jump is between stage 2 and 3. And this is where actually electrification becomes less efficient as opposed to what we usually think of heat pumps. So the increase of electricity is much higher despite a small reduction of final energy consumption. So in terms of sector focus, the highest decrease, as we could really estimate, would be the food, beverages, and tobacco. So we can actually decrease their energy consumption by up to 44%, which is really consequent for such a sector. And also chemicals and other industries and metal and equipment manufacturing have some quite important decreases, but not for the same types of stage reductions. So important reductions for different sectors, but not equal reductions. So for example, basic metals or non-metallic minerals. So the sectors that are really heavy and high temperature don't have such a high reduction. And in terms of emissions, so we can actually quarter energy emissions. So really the core aspect of electrification, which focuses on combustion from fossil fuels, and reduce them actually by up to around 45% using only mature technologies. And what we see is that there's really two main things that are really important in terms of emission reductions from electrification. It's that process emissions still remain. So there is a need for alternative technologies to cover these process emissions, or electric technologies that can directly implement themselves within the process. Some technologies do exist, such as, for example, in the chemical sectors for ammonia production, but it's really difficult to find actually data and economics for these technologies. And another aspect is there is quite an important focus on the importance of a low carbon grid. As you can see, if the grid is not cleaned up, so if we have the same grid as today and not 12 grams of CO2 approximately per kilowatt hours, we can have an increase of more than 1 megaton of CO2 per year. So it's really crucial to have a decarbonized grid. And focusing again this time on industries, the highest decrease again is on the food, beverages, and tobacco. We can decrease their emissions by up to around 90%. Followed by actually metal and equipment manufacturing, because it's mostly processes that require heat, but not really specific processes that can be electrified, and basic metals as well, despite having a small reduction in final energy. So we do see that there is an importance in electrification for specific sectors, especially low temperature sectors, which have the highest potential for emissions reductions. And however, the results will really be dependent on what type of stage of electrification we're at. So for example, food and beverages, it's mostly stage 1, stage 2. So mature technologies, whereas non-metallic minerals, chemistry, or basic metals, it's stage 3, so much higher temperatures. So this will be really important in the economics and the feasibility against alternatives. So now that we've actually covered the potential, we can actually look at the conditions for electrification being competitive. And so the first thing is that success. So what I mean by success is really like being competitive against other low carbon alternatives or fossil alternatives. It's actually highly dependent on the electricity's competitiveness. So how performant electrification is and the cost of CO2. So looking on the left side, we actually gathered a few actual projects in Switzerland, industries on heat pumps, for example. And the coefficient of performance of heat pumps is critical actually in terms of economics of electrification, because heat pumps have a high capex. So having actually efficient processes and reducing electricity consumption and overall energy consumption is actually really beneficial for the economics of electrification. And secondly is actually focusing on the CO2 tax. So when we reach approximately process levels of around 100 degrees, electrification is in the same cost range of gas in terms of levelized cost of heat. So a CO2 tax would be really necessary to actually do a phase shift and actually cost and render the electrification competitive. So these are really like main aspects, which is performance and CO2 costs, but not only, we'll see later on. So what we did is that we actually performed a marginal abatement cost curve for electrification for Switzerland's industry by dividing all the sector in the different subsectors, as well as the different use cases, and energy vectors. So what we can see is that on average, with only mature technologies, we have an abatement cost of minus 64 francs per ton of CO2. So what does this imply? It's basically that electrification is actually competitive, and we can actually save money by electrifying our processes. So if we dive a bit deeper in each of the sector, we can understand where does this result come from. And mainly the main sectors are, as stated previously, it's food and beverages and manufacturing, metal and equipment manufacturing. So these are the sectors that are really competitive, where electrification is competitive. And we have abatement costs of approximately between 150 and 200 francs per ton. So this is really competitive against alternatives. And these are the ranges where heat pump exists. And when we go actually to higher temperature sectors, such as chemistry, pharmaceuticals, non-metallic minerals, we notice that actually the curve shifts and we go into positive abatement costs, despite having, for example, a CO2 tax of 120 francs. We notice that actually it's not competitive against the current baseline. So this actually suggests that where electrification technologies are mature or performant, we do have some competitiveness for electrification, mostly pulled by heat pumps, by industrial heat pumps. And when we go into electric technologies that aren't as efficient, abatement costs become really high. And so the idea actually, so the past graph was focused on using average costs for Switzerland's energy vectors. So the idea was to actually look at what would be the break-even prices points to actually see when electricity would be competitive against alternatives. So what we did, for example, here is to look at the break-even point based on the price ratio of gas to electricity, upon which electrification becomes competitive for a specific sector. So for example, let's say the 0.3, which is process heat up to 100 degrees Celsius, becomes competitive when we have a price ratio of around 0.3 of gas to electricity. And if we actually look at historical values of gas to electricity price ratios, we do see that actually space heating, hot water, as well as process heat up to 100 degrees were always competitive since 2011. So let's say maybe not always competitive, but given the current costs of heat pumps, they are competitive whether we have prices from 2011 to 2015, 2021. I'm not even talking about 2022 when gas prices exploded, because at this point, even process heat up to 200 degrees or 400 degrees can become competitive, but since it's an anomaly, we're not looking into it. And another interesting aspect is actually we decided to compare the gas to PV plus battery systems for industries that actually want to have their own systems. So we do see that starting in 2020, 2020-ish, the same uses become competitive as well against alternatives such as gas. So the conclusion is up to 100 degrees with current technologies, electrification is competitive, whether we had historical prices or today's prices. And the rest will need some CO2 tax or other innovations in technologies to render electrification competitive. And so, as I've talked, I've given a few hints before. It's regarding industrial heat pumps, actually. So they are actually the main powerhouse of electrification, especially in Switzerland, which has quite some low temperature sectors. So they constitute around 86% of the energy savings that the industry could offer, and are capable of actually saving 5.3 terawatt hours of gas, and which is around 50%, which is really not negligible, and around 1.7 terawatt hours of light fuel oil, and only represent 23% in the increased electricity demand. So here, electrification through industrial heat pumps is really the core aspect in terms of economics. They actually offer an electrification potential for the industrial landscape that is competitive. And the idea was to actually delve a bit deeper into how to render industrial heat pump competitive. So this time we not only looked at the gas to electricity price ratios, but we also looked at the required temperature lift that the heat pumps could offer, and looked actually at what break-even price points we had. And this is only the marginal break-even cost curves against gas boilers, which are the main technology that is currently used in the industry. So if we first look at the process heats up to 100 degrees, so we see that as the graph could state, as the previous graph could state, it's always competitive, whether we're at a temperature lift of 20 degrees or 80 degrees, given the historical ratios for prices and the average. But if we look actually at 100 to 200 degrees with steam generation, things become tricky. So we do have conditions where electrification is competitive for around, let's say, up to 40 degrees of temperature lifts, if we use the historical lowest point of gas to electricity price ratios. And as said previously, the usage of a CO2 tax of 120 francs per ton, we could really decrease actually this curve and render electrification much more competitive. And so here, an important aspect is when thinking of industrial electrification, an important point would be actually reuse of heat. So this is an important aspect that we did not look into. We just looked at the brute energy demand, let's say it like that. So reuse of heat and hence reducing the temperature lift could render industrial heat pumps really competitive, especially at the temperature ranges of 100 to 200 degrees. So now that we've actually seen the conditions for competitiveness, we can focus again on the food and beverages sector, which was really like, let's say, the star of the show for the industry sector in Switzerland. So we have actually, considering all technologies, not only heat pumps, we have an average abatement cost of minus 113 francs per ton of CO2, given average historical conditions. So, and mostly given by, as previously stated, industrial heat pumps. So here, there is really an important aspect on industrial electrification, and also a big potential for emission savings as well as cost savings through electrification. So not only positive aspects, but we do also have some challenges with regards to electrification. So the first point is electrification technologies require substantial investment costs with regards to standard boilers. So given the a small market analysis we did, we noticed that industrial heat pumps investments, so not only the equipment cost, but and also installation and labor costs, we're at around 800 to 1,200 Swiss francs per kilowatt of heat capacity. This does not include heat pumps over 100 degrees because they're not present on the Swiss market. Whereas gas boilers and light fuel oil boilers have investment costs that are lower than 200 francs per kilowatt. So we do see a huge gap with regards to investment gap. So despite having overall economics, so let's say a levelized cost of heat that is more performance, there is the issue of investment costs for industrial sectors, which usually tend to look at payback times of less than 3 years. And so having such high investment costs actually hinders a bit of electrification because we can reach payback times that are really high. So this is really an important aspect that needs to be integrated when promoting electrification. And the second aspect is actually the electricity prices. So looking here at the day, I had a spot market on the Swiss electricity market. We do see a lot of volatility, especially since the end of 2021 with an explosion that occurred in the electricity prices. So industries actually tend to focus on the quality of electricity, which is really crucial. And it was quite tricky for the last 2 years, as well as the stability. So let's say the volatility of electricity that is really important for industrial consumers, and obviously the price of electricity. So these are really specific aspects and important aspects that could hinder electrification in terms of economics. So overall, if we resume the presentation, so electrification of Switzerland's industry is possible, technically possible, and realistically, it could be electrified up to 73% with 56% from existing and mature technologies. And electrification can lead to a decrease in energy consumption and can halve sector emissions. And overall, the electrification comes at a cost of 100 francs per ton of CO2 abated, which is heavily skewed by non-mature technologies, as we've seen it on the marginal abatement cost curve. But with current mature technologies, the cost of abatement is negative and hence competitive, and it could decrease emissions by around 30%. So overall emissions, not just energetic. And industrial heat pumps are the main powerhouse of electrification. They could save around 50% of current gas consumption and around 70% of current LFO consumption. But electrification really focuses on specific conditions for it to be competitive, which are performance, the cost of electricity, and the cost of CO2. So yeah, any questions? And thank you for listening.
Thank you very much. Thank you, Kevin.